Okay, so we ready? Everybody uploaded it? Yeah. Okay. Were you guys ever find it? Okay, so part one. Let's start out. What am I going to do?
Did our formula first?
Okay, so let's use our formula first.
100%, but AlNO3. And then I think that's in parentheses. Yeah.
Okay. Which part?
I think the whole thing.
This whole thing?
Yeah. No, I wasn't sure if it was that or if it was the NO3 only.
Anyone help out? It's the NO3 only. Why it's just the NO3 as a 3 with parentheses? Nitrate has a -1 charge, so you're going to need 3 of those to balance out. Okay. Anything else I need to add to this? 8%. Yes. You're the only person that's
I did
strong enough to sit there and tell their answer. Everybody else is trying to be scared. I know Christina's going to help me with the next one. What are we reacting with? Really use your parentheses for your diatoms. Or polyatoms. Okay? And we're making
the AO and then you get the other two on the outside or on the inside.
AL
One is the SO4
SO4
plus and NO3 in parentheses 3 and aqueous still.
NO3 in parentheses. Down, you said in parentheses.
Yeah, with 3.
What are you missing also? Missing something.
That's where specifically.
Sodium. This is the sodium, right? So sodium is going to pair up with what is the charge on sodium?
+1.
+1. What is the charge on nitrate?
-3.
-1, +1, -1 to balance out completely, right? So then I don't need that 3 of these. Okay. So
Does it matter which one goes first?
it does. Yeah, because if you're writing it the other way around, you always want to put your positive first. That was always going to go first, or your positive ion goes first. Want good news before the bad news, right? Positive first. Okay, that's also a tip for sign G, because Google will flip it sometimes. And so when I'll have certain questions on exams that. But positive always goes first. Okay, so this AlSO4, is it going to be solid, liquid, gas, or aqueous? Aqueous? And is that balanced? Written correctly. Just says the formula written correctly. Why is it written correctly? What is the charge on a liquid? 2. So +3 - 2. Does that equal 0? So how many aluminum should I have? I should have 2. And then how many sulfate should I have? Okay. I'm myself enough room so you guys can see that. Is it balanced? Is the chemical equation balanced? What do we need to do to balance it? I need to add more aluminum or sodium? What do you mean by that? I'm going to put 2?
No, another one.
Over here.
Yeah.
2. Okay. So that gives me a total of how many nitrates? 6. So I have 6 nitrates, so then I should probably have what here. If I want 6 nitrates, how about a 6, right? And then over here with my sodium sulfate, what do I need to do to balance that out? So then that gives me 6 sodiums, 6 sodiums, and then that gives me 3 sulfates. Right? Okay, now we have a balanced chemical equation. Okay, so if we were doing total ionic reaction. What does it do with that? That. Okay, so tell me what I need. Give me numbers. 12 plus 6 nitrate. Okay. You have to drink just I know that you're putting them in, right?
Plus sodium constant.
6 sodium positive charge. Thank you. Plus. Okay, so what do we know about this? Yeah, sodium will be one spectator. Anything else? Yes, the nitrates will be another spectator.
Everyone's a spectator.
Everybody's a spectator. So in other words, we're not going to get a reaction out of this. So we would write no reaction. Say everybody's a spectator. It's important. Yeah. Everybody stay on the wall.
Can you go over the spectators again? Does that have to do with the partners?
Spectators, yeah, so if nothing partners up, then yeah, right? Nothing precipitates out, then it stays aqueous. That means it's just sitting in solution, it's not doing anything. Okay, so all of those things are soluble. If you take a look at your solubility table, did you guys take a look at your solubility table?
Yeah.
Right? And then that's how you determine that it was aqueous, right? And so that one should have been the first thing. That means that everybody's going to be affected. That means that there's not going to be a reaction. Okay. So in other words, everything just kind of sits in solution. So spectator is like what you get in the beginning. It's exactly the same that you get at the end. So exactly the same on both sides. So no reaction curve. Does that make sense? Okay, questions? That's right. Yeah. If you have everything that is on both sides of the equation, then there's not going to be a reaction. Solid or gas, then we know that you have a reaction. Okay, second part. So is it okay if I erase this for sure? Second part. Part 2. It says determine the number of molecules in 36.36 grams of water. Where am I going to start? So I have 36.36 grams of H2O. So how would I be able to determine the number of molecules?
So molar mass H2O.
Molar mass. What is the molar mass of H2O?
32. Around.
Are you sure you don't put money on that one? Put your money. I got money up here.
All right.
18.
Or 254?
18 grams for 1 mole. Base flow roughly, right? Okay, so that gives me the number of moles.
And then you do the molecule, which is 6.022 times 10 to the 10. And then
So we're gonna have 6.022 times 10 to the 23rd. You guys tattooed this weekend, didn't you?
yeah, honestly.
Oh. What did you guys get? $50 times 10 to the 24. So when I was in Japan, we had a hard time. It would always T nights like 50. Okay. Piece of cake. Okay, so today we're going to get started on that concept about acids and bases and everything like that. I also want to talk to you guys about the different types of reactions. It helps to know the different types of reactions. Okay. So I'm actually going to show you a slide that I use in my 2A class. Yeah, 2A class. This is really a slide that shows things a lot better. I can put it on the board and then write all of them up. It's not as pretty. So have a quick answer.
So you normally have these little
Yeah.
Are they already organized in a specific way?
Yeah, they were, but you could reorganize them.
Okay. Just want to make sure, because I was gonna take them out, but I was like.
Yeah, if we could get them in a nicer, bigger box, because those are separated, or if we could put those in a box within a box, so we have them all together. So,
Okay. All right.
anything to make my life. Okay, let's see. Did I happen? Okay. That installation. See. Go to. Oh, they took the call. Perfect. Okay, so let's see. Okay, so I'm going to go to reactions. So there are 5 different types of reactions. We'll talk about 4 of them, and then I'll write the 5th one for them. The 5 major types of reactions are a decomposition reaction. So a decomposition reaction is where you have a product that's together and it's able to be split up into 2 or more parts. Okay. So this is an example of it right here. Okay. And so that would be the decomposition of water. Right? So if we have water, we're breaking it up into its elements. That would be an example of the decomposition reaction. So, okay. Does that make sense? Simple? Not too hard. You guys don't have these slides. So sometimes a decomposition reaction can be reversible. So in the case of breaking up water, it can actually go back. Now, if it's a reversible reaction, that means that we use an arrow going in both directions. This is also what we use for it's balanced, yeah. So in other words, what's happening is that the reaction is able to go in both directions. So you're able to make the product as well as making the reactants. And so depending on what's happening in the reaction itself, which side will be favored, which way the direction is going to go. Okay. We'll talk more about that in the second semester. So, but I just want to kind of introduce it to you right here. The second thing is a single replacement reaction. Single replacement reaction is often a redox reaction or an oxidation reaction. We'll be talking a lot about that. So the way I like to think about this is that you're replacing one of your element for another element. Okay. So in other words, you're replacing, to be specific here, you're replacing B for A. So I also say if I'm getting rid of my old girlfriend or getting a new girlfriend, so it's another way of replacing it. Now the key is that that element has to be similarly charged. Like for instance, you're not going to replace sodium with chlorine. Sodium is actually a plus, and then chlorine is going to be a minus charge. So it has to be replaced by like things. So a metal has to replace a metal or hydrogen. Okay. We'll talk more about that here in a minute too. Okay. So an example here is where we have copper, nitrate. Copper is going to be replacing the silver and silver. So in this situation, you guys can see where the copper actually replaces the silver. So that's actually being the measurements that are going to be taken away from copper. You guys are already familiar with the double replacement reaction, right? Or I call it the swingers reaction, right? Where you have partners changing. Okay. So here, in this case, we have sodium chloride being replaced with silver nitrate, and we get silver chloride as a precipitate, and we get sodium nitrate as our other. So that brings us to acid-base reactions. But then now we can go back to our slideshow. Well, I didn't tell you the fifth. The fifth reaction is the combustion reaction. And you guys are already familiar with combustion reaction? I'll write that one on the board because I don't have a slide. A nice slide. Working on it. The combustion reaction is actually of organic material. So all it is that oxygen plus the hydrocarbon. The hydrocarbon is just a compound that has hydrogen and carbon in it. Awesome. Anytime that you have a combustion reaction, getting rid of carbon dioxide, okay. So, as I said, it's also called the oxidation of hydrocarbons. It's called the oxidation of hydrocarbons because you're adding oxides to it. So you use oxygen to break up that hydrocarbon to make carbon dioxide. Okay. Questions? fire. Yes, that is the premises of fire, combustion, right? Combustion is fire, right? Okay. So those are your 5 reactions you need to be familiar with. And we're going to be talking more about those when you guys have done the plate assays. Have you guys done those plate assays yet? And then some of you and then you guys have done. You guys have done it. You gotta have that. So, in the case of your acid and base reaction, so acid and bases, I'm gonna go back to the board here in a minute. We're gonna be basing our definition of an acid first on the Arrhenius definition, okay? And let's spell that for you.
So then, look at this definition.
Is an acid is a proton donor. And a base is a proton acceptor.
Okay, so I want you guys to think back to this.
So if we're talking about protons. You guys remember how to determine how many protons, electrons, and neutrons are in an atom, right? So if I'm talking about how many protons does hydrogen have? How many neutrons does hydrogen have?
0.
Okay. What about H plus? How many protons does H plus have? Okay. How many electrons?
0.
Okay, so we know that a hydrogen atom
Proton.
it's just a proton. Okay, so when we're talking about a proton donor, we're making reference to the H plus ion, the hydrogen plus ion. Okay, now the hydrogen plus ion, when it's in an aqueous environment, what it does, it attaches this here is called the hydronium. Okay. So often when we're making reference to the hydronium ion, all we're really making reference to is the hydrogen ion. Okay. Does that make sense? Okay. So for simplicity and to make it easier for us to keep track of it, I will often use H plus, even though this is what forms when it's in an aqueous environment. Okay. So So, but I'll always make reference to this, because it makes it easier to keep everything balanced. Okay, does that make sense so far? Okay, so if we think about an acid, we define acids in two different forms. There's a strong acid, or there's a weak acid. Strong acids are going to be those acids that completely dissolve. Another word that we'll say is that it will ionize. So that basically means that it'll break down into its ionic parts. So we use hydrochloric acid as our example, since brought it up. Okay. So if we have the H and an AQ, that makes it an acid. You guys already know how to name acids already, right? I think we've already talked about strong and weak a little bit. So the arrow basically shows that it's a complete dissociation. And that's going to be kind of important for us to understand that it's completely dissociated. It's going to break up to its ionic components. So you have the H plus and the Cl ion. You guys know when I make reference to this, I'm making reference to what? The hydronium ion. Okay. Now, a weak acid. Can I erase this part? We got this.
Yeah.
A weak acid will partially so we'll often write with two arrows. Typically, the one that's being favored, the side that's being favored, being drawn bigger than the other.
My favorite.
I'll explain this. Favorite meaning that that's the form that it likes. Right? So the acid itself, so for instance, this is nitrous acid. Nitrous acid prefers to be together, right? Rather than the H plus coming off of it. So it's going to have more species of this in solution than it's going to have in convert. Okay. So there's going to be very few of these in solution, but the majority of it is going to be this. Okay. Yes. And it also favors one over the other. That's why we do the link. Problem is that when we're writing it or typing it up, if we don't have a key that's double arrow in some cases, or if it is, we have a key that's double arrow, they're always even. They're never different side. So we have to pay attention to the constant, which would be equilibrium constant to see which side is favored. Okay. We'll talk about that. We'll talk about equilibrium. Okay. Yes, that helps us with So, strong acids typically end with IC, ick, right? Weak acids will end with OUS, so those are typically going to be weak acids. Also, weak acids are going to be carbon-based acids. So, for instance, citric acid, even though it ends with IC, it's a weak acid because it's a carbon-based acid. Okay, so carbon-based acids are typically going to be weak acids. Okay. Okay. So, for instance, phosphoric acid. Is that going to be a weak acid, or is that going to be a strong acid? Acetic acid. Sure. Okay, it has ick in it, but is it a carbon-based acid? What is acetate? Looks like your polyatomic ion table. It has carbon in it, so it's going to be a strong acid, it's going to be a weak acid. It's going to be a weak. Sure. It has carbon in it, so then it's weak. Okay. So if it has ick, we want to make sure that it doesn't have carbon in it. If it has carbon in it, it's a weak acid. Okay. Phosphoric acid.
Strong.
Strong. Thiocyanate acid. Okay, so that's that, right? Pretty simple. Okay, now again, the difference between a strong acid and a weak acid is, well, carbon, what else? What happens in a case, what is the characteristic of it? Let me change that. Characteristic of a strong acid. It completely dissociates, right? So strong acids completely dissociate, where weak acid, it mostly partially dissociates. Okay. Okay, now that's going to be important if we're doing dissociations, right? If we're doing complete ionic dissociations. Right? So we're not going to get complete dissociation. So we know we're going to get some of that in our main thing, right? So we can't do total ionic equations with something that's partially dissociated, right? Does that make sense? Okay. So we would have to know more about the compound after that. Okay. So we typically don't do that with this guys. Okay. We do it with this guys. So when we talk about acid and base reactions, right? And we're also getting reformation. So strong bases are going to be bases that have strong base is going to be a base that completely dissociates. A weak base will also partially So examples of a strong base is going to be sodium hydroxide. So the hydroxides, when they dissociate, are going to be strong bases. With two metals, some of the two metals will dissociate. When we start getting to the transitional metals, they don't dissociate, right? So those guys would be examples of weak bases, right? Because you don't get a complete dissociation. So if we took a look at that solubility table, right? We can use our solubility table to help us determine whether or not we get partial dissociation or complete dissociation. So like for instance, aluminum hydroxide, is that gonna be a strong base or is that gonna be a weak base? A weak base. What about strong base? Yeah. Association. Yes. It's actually a weak acid and a weak base. We'll talk about that. Okay, so we know that aluminum hydroxide this so we know we're not going to use that for a total ionic type of reaction. Right? Because that would be- Okay. Another weak base that I want you guys to keep in mind. Ammonia is considered to be a weak base. Baking soda is sodium bicarbonate. So this guy actually plays both roles, right? And then the H that's there that acts like it's an acid. So it'll act like an acid sometimes, and it can act like a base, depending on the circumstances. Okay. So that's the reason why if I spill acid, guess what I'm putting on? Baking soda. If I spill bases, look, guess what I'm putting on? I don't have anything else. Baking soda. Yes.
For the basic, would apply the same rules? For example, if it's a base, strong base will weigh.
No, it doesn't. We don't have the same rule. So the only thing that is a proton acceptor. It's able to accept H plus. Well, if it's OH, well, that guy really wanted to accept H plus, right? Because if I add H plus to this, it cancels out and it becomes what is it? H2O. Okay. So prime acceptor, right? And then that's the same thing here. We add H plus, it becomes, which is like, oh, cool, I can do that. Okay. Does that make sense? So that base, right? It's going to be able to accept H plus, right? So it becomes so it'll become H2CO3, which is a weak acid, right? Carbonic acid. So it's not going to want to separate because it's a weak acid, right? Now, if it's an acid, then we end up separating. Let's get him a. Because then we'll just get rid of that H plus. So if I have I have a strong acid and a strong base. What's going to happen? What are going to be my products? conventionally first. Solid, liquid, gas, or aqueous? Aqueous.
That's what I'm not sure.
Well,
H2O. Solid, liquid, gas, or aqueous?
liquid,
Okay. So then if we did the total ionic equation on this, it would be plus plus the yield plus the minus and H2O. Okay.
Can you explain why you have to separate the H2O?
Either solid, liquid, or gas, right?
Oh,
So once it's together, it's not going to separate. Okay. The only thing that's going to separate or dissolve is the precipitate. Okay, so spectators, who are the spectators here? Spectators.
well, they're all spectators.
NaCl,
That's exactly the same on both sides. Sodium A cube here, sodium A cube here, so that's spectator. Okay. But they're exactly the same. Okay. What about the OH bonds?
Cl.
What about H plus? So you said Cl. So these are the people who came to the party that hooked up. You know? Mingle. Single, ready to mingle. Okay. Preguntas. Okay. You guys want to take a break? We're a little behind, that's okay. We'll catch up real fast. The next part is last thing. My brain's like a second. I like the immediate. Okay, so let's go ahead and take a, I'll give you guys a 12-minute break. So I'll meet you back here at 2:30. You guys gear up. So you guys get back, gear up, start looking good.
find out stuff. The acids and bases are defined. We flashing back to like at the top of the world, like see what's the hydrogen that makes the pH.
So we don't need. So we don't need.
So everyone's sitting here today. No, I'm half tempted to get this. Slice. Okay, organic plus.
Yeah.
Boy, I spent so damn long with this hair.
So you're off.
Your art style isn't just general shape of hair. No, it just has fucking. Because technically, there's two categories. Don't talk about the dad. We don't talk about the dad.
I was bringing it up.
I hate it. It's so bad. For years, there was like, for literal years, people have been drawing grown-up Naruto with like shoulder length hair. It looked amazing. And then fucking Boruto comes out and he's got a buzz cut.
Bet you do.
Like, how could they do this to my son? He has a receding hairline. He's in his 30s. No, he's probably not in his 30s. He's probably closer to 40, but like still. Still! Put my bag.
Also, I trust myself. You're excellent, buddy.
Sometimes I was like throw it back hard.
You would do.
But I want to get every drop in there. But he was going so fast. It's right down the reaction. He was going so fast.
I think he was writing stuff, and then this is what I got, and I don't understand what I wrote.
So far.
Yeah, that's fine. I still don't even understand it even then.
I will explain it to you.
But you like he's gonna say that. Strong bases. Dissociate.
Did I give you guys the table? Did I give you guys
The
Oh, you weren't here, so you don't get it.
plate with
The plate,
yeah, our
You-
group did.
your group did.
Yeah,
yeah.
what's the-
So you guys are gonna do another plate, but you guys are gonna do
Oh,
single displacement.
It's literally just dropping it like one at a time and then saying if literally anything changed. And then the table is just like reaction or reaction.
So did I give you guys? the
And then you
single displacement
probably want
class?
to take a picture of the thing so that well we have to actually
Yeah.
keep the plate anyway.
I
So
understand.
later, but initially it's just
Okay, so I did give you a
each
letter.
well has like here's the car.
I think that not a lot of people are here because it's like that.